as I said, thanks to all the organizers. I think this is a wonderful idea to combine agent-based modeling and the more empirically oriented network modeling tradition. Because both of us work with, say, both of the disciplines work with simulations of complex network structures. And I think there is a lot to the development going on in parallel and thoughts developing in parallel. And it's good to, say, kind of cross-fertilize and come to know about how others think about the same problems that we in both communities are facing. That being said, my talk is about, actually it is sort of workshop material. So it is quite introductory. So in that sense, I think it is reasonably, it's a good start for such a session, I would say, because it might establish common ground. And I hope to also set some awareness of concerns that one might have with applying the empirical network models, so exponential random graph models, stochastic actor-oriented models, in simulation framework. So there are some principled problems that I think everyone using these methods for simulation should be aware of, and I hope to make clear what these are. It's not so fundamental, it's not so complex. It is actually quite fundamental considerations, so I think, it's good to do this at the beginning. Now, that being said, I think I need to go elsewhere for switching. This is the overview. I don't really have a take-home message. Basically, I didn't finish the slide and I'm not so clear, but they will grow while we are following the rest of the slides. I want to talk about what stochastic network models are, then simulation-based inference, the idea of it, then basically the separation of control parameters and manipulated parameters. This is in the empirical tradition, kind of a unified treatment, which is different in the agent-based modeling tradition. And then I want to, basically talk about 3 different types of simulation studies that people have been doing and that one could do. And of course, there might be different and there might be combinations, but these are the 3 that I see clearly in front of me. And I just want to walk through a couple of those. And while doing so, say, make some observations. Okay. What are stochastic network models? Well, they were developed in a classical statistical tradition. The purpose is the empirical testing of hypotheses. Well, like you know from regression analysis, you have the question, does income affect education? And then you run a regression analysis and do the testing and you get an answer, at least a statistical answer. And in the same way, the stochastic network models have been developed for facilitating tests of micro-level network mechanisms or regularities, I probably should say. And these could be about the structure of networks. I give here this blue colored example of does an indirect connection through these solid blue ties, when there's a friend of a friend, for example, does this lead to the formation, or does this actually make it more likely that there also is a direct tie? Well, this is a typical closure question, network closure. This is about, having hypotheses about what governs networks as such, how they look like. There are models also for dynamic networks. Second example is about homophily. So when 2 nodes are of similar quality, is there a higher likelihood of them getting connected over time? And finally, there might be studies of dynamics, not off networks, but on networks, when you have individual properties of actors in the networks that might change in response to what goes on in the network, like contagion processes unfolding. And in this little diagram, you see here 1 person being connected to 2 people who are red, changing the color to also become red. Now, this is basically the type of micro mechanisms that we are testing with these models. And concretely, the structure of networks typically is analyzed with exponential random graph models, the dynamics of or on networks, typically with stochastic actor-oriented modeling. However, there are variants of each model that also cover the other type of data structure, whether dynamic or static. So this is two approaches, basically. I don't want to single out anyone for this presentation purposes. The examples that I give will be from the stochastic actor-oriented tradition, because this is what I'm most familiar with. Okay, so this is stochastic network models. The aim is empirical testing of micro phenomena. So this is not about simulating, or this is not essentially about studying anything on a societal level. However, what these models do is, because they are models for complex data sets, and because they are, well, characterized by what in statistics we would call an intractable likelihood function, which means given a data set, we cannot just calculate its likelihood. We need to approximate it in a complicated way. Because of this, these models typically are estimated by simulation-based inference. So this is a technique of statistical analysis that exists since the early 1950s. I give here three important estimation algorithms that were designed back then. Metropolis is maybe the most famous one. This is was developed in the atom bomb project Los Alamos. The tellers are famously also co-authors of this article. And this grew into Markov chain Monte Carlo estimation later on. And the other two, well, they are different. They are not Markov chain models. I want to give a brief impression of how simulation-based inference looks like, because I think this gives some intuition of the problems that one may have with working with these models for simulation. What you see here is, say, the initial situation. Suppose you have observed a data set. This is here the red dot in the middle, observed data. I put it down here as a point in two-dimensional space. Of course, this is a very complex data set. It's a network, or maybe it's a network, the end result of a network evolution process. But we project it here to a two-dimensional subspace, which consists of the number of edges and the number of diodes of that network. And for estimating our models with a parameter that should actually govern the tendency to form edges or to reciprocate, we need to start somewhere. So typically we take some initial values, we then simulate data sets. And what you see here is just a simulation of artificial data sets, the black cloud in the lower right. And of course, this is way off. Now, this is not in any way close to the observed data point. It generates too many edges and too few reciprocated edges. So the parameters need to be changed. And this is what the stochastic estimation algorithm does. So after one iteration, it may look like this. And so things get a bit closer to reality. So the model fits the data better. And after convergence of this algorithm, for example, these equations here need to be solved. The observed data needs to be the expected value of the simulated data. And what you see here is how such a solution looks like. And one thing I would like you to note is that these simulated networks that you see, the cloud of black points, they actually indicate some correlation between the two statistics, the number of edges and the number of diodes, which is sort of logical if you think about it. The more reciprocated ties there are, the more ties there are. So this is what you see in this strong positive correlation. And this high correlation actually is a message that we should take into account for later on. So let me move on. This is basically the idea. So you simulate networks You compare them with the observed data point, you adjust the simulation model, the generative model, such that you get the correct expected value. Okay. And the width of the simulations can be used for assessing standard errors, and then you can test your hypothesis. And this is basically the idea. But of course, we get a lot more than these test results. We don't only get parameter estimates and standard errors, but we get all the framework of generating artificial data. And we get the clouds of simulated data under different scenarios. And this can be used also. This can be used for actually macro level analysis, because we have complex data, we have macro system level observations, or well, simulations that we have generated, like in social simulation research, and why not make use of them in a similar tradition, trying to explain macro outcomes. So we can use them, these models, for generating macro level outcomes. Of course, they all rely on their own assumptions, on their parameters, and on the data. And if we then compare different simulation scenarios, like one would do in an agent-based modeling study, then that means we need to manipulate these dimensions. Normally, we don't manipulate the model assumptions, but we manipulate the parameters of the data. And this is basically what I want to talk about, what strategies there are for doing this. Okay. And well, this is a comment I don't want to go too much into, because it is a whole different can of worms. There's also this causality interpretation. If you change stuff and things look different than they do as we observed, we could actually talk about counterfactual causality in these kinds of studies, but this is a different issue. I don't want to go into the details here. Now, if we want to study emergence, basically macro phenomena that are consequences of macro level assumptions that we have not anticipated when just looking at the micro level, then it is good to first take a closer look at what actually we consider to be emergence. I would say, but people might disagree, I would say that emergence is always conditional on a model specification, at least in our framework here. So we can say transitivity emerges when there is no explicit transitivity term in the micro model, but, for example, homophily terms. If the ethnicities always choose individuals of same ethnicity choose each other, that will eventually lead to triangles as well inside the ethnic groups, and then transitivity emerges. However, you could just as well model transitivity explicitly by including a transitivity term. And this is why I would take a kind of relative definition of emergence, conditioning on the micro model. Something might emerge or not. Okay. And that leads to the question, before running any of these empirically calibrated simulation studies, I mean, the big advantage of running such models over running just any simulation study is that you can actually calibrate them to data sets, making them maybe a bit more realistic or empirically anchored. But you need to always ask, what actually are the outcomes you want to study, and how do you deal with emergence? And also something that's not on this slide, what do you take as things you want to account for? What are the control parameter dimensions, and what are the manipulated ones? But this will have strong consequences on the results of your study, as we will see. Oops. Now, the network features, like we have just seen, the edges and the reciprocated ties that I was showing you, they are located in a parameter space, and there can be many more. There can be transitivity, homophily, there can be influence parameters. This parameter space we have sort of under control. This is the input from which we simulate data. It is seemingly flat, seemingly orthogonal of dimensionality that we choose. So this is sort of under control. When we use such a parameter configuration to simulate data sets, we get what I would call here a surface, a curved surface in a much higher dimensional space. But typically it is curved, typically it is correlated, so the parameter dimensions are not orthogonal anymore. I might increase the density parameter, which governs the number of edges a little bit, but that will also increase the number of reciprocated ties, although I have not increased the reciprocity parameter. But these model internal correlations that we have seen in the earlier slide, this is something that establishes some problems here for running the simulations in a very simple way. It's a curved space in the expected values of simulated data. Okay. This is kind of add-on how this is called in the exponential random graph modeling tradition. We talk about natural parameterizations and mean value parameterizations, which correspond to this flat, seemingly flat space on the left or the curved space on the right. And there is some literature related to this. Now, I would say there are three basic types of empirically calibrated simulation studies. First type, we just naively manipulate parameters. And I would argue that this is not what you should do. Second type is you do that, but you do that with the aim of manipulating the outcomes in the curved space, in the space of expected values of statistics, while accounting for the controlled dimensions on that curved space. That means you need to re-estimate models each time you manipulate parameters. And this is something that I think really needs to be done, and that yeah, should be one of the take-home messages here. I will show in examples why I think so. And then third type is manipulation of input data, keeping everything as estimated. So we have different input data, and then longitudinal model might translate them into different outcomes over time. And so this third type basically refers to stochastic actor-oriented models, or models that have a time dimension on. Let's go over that. Simple parameter manipulations. Idea is you estimate the model, you make model variants by manipulating parameters of interest, you simulate networks from these model variants, you check what they predict in terms of the macro feature, and that's it. Well, I didn't show the Coleman boat before. This would be the micro level of the Coleman boat. So the assumptions and the feedback, the micro level decisions, B to C, and the feedback. Example, suppose we want to study how intergroup integration depends on the relative strength of homophily. So we just manipulate one parameter. We calibrate a model with a homophily term to an available data set. We change homophily in steps, make it bigger or smaller, and we check how the outcome, for example, number of cross-ethnic or whatever ties there are, and see how that, say, changes given the size of the parameter that we manipulated. Very simple. Actually, I do the same thing twice here. Once with a so-called same X parameter in the Siena framework, and I estimated the same model with the sex similarity effect, which is technically speaking the same. It does the same thing. Also, in terms of testing, it means the same thing. When your sex is similar, this is a 0, 1 dummy variable. It's the same as when you have the same sex. However, the difference is that the sex similarity effect is centered. So actually, the estimates are relatively the same that as you have seen, but because the one effect is centered and the other is not internally, we see that the density parameter, the density estimate, differs. So the fact that the effect is centered needs to be counterbalanced by a different density parameter. And this will show back in the simulations because the density parameters for different simulations of equivalent models will look different. And these are these nuances that you need to think of when using these stochastic network models. This here are simulations of the number of, number of cross-gender friendships. Now this is gender. Depending on how much the parameter of gender homophily was changed. To the right it was increased, to the left it was decreased by the factor indicated below. And we see, well, there is some sensitivity. So the more homophily there is, the less cross-gender ties there are, the less, the more heterophily there is, the more nice. However, if we take the better fitting or the probably better model, then we see that the sensitivity is much stronger. So this shows that working with centered effects seems to lead to quite different and sort of better simulations. The manipulation is stronger. Reason is that, the way how the number of ties is affected is different. If we take a look at the number of ties, this is what the worse model parameterization would suggest, and this is what the better would suggest. And the interesting thing to note is that even the better model still does not give us a flat line. So we have increased the sex similarity parameter, or we have decreased it to the left, and the number of cross-sex ties goes, well, shows that, well, the number of cross-sex ties we have seen on the previous slide. The total number of ties is actually increasing with that parameter, and it is decreasing when the parameter decreases. What you see here is a model artifact. It's the internal link function that the logistic curve that we use for the multinomial decisions in that model actually implies. So this is actually not something that we would think is a result of the simulations, unless we have very strong beliefs in the preference interpretation of such a model. But actually, I would argue what we want to see is simulations where when you manipulate the one, the gender homophily dimension, you should actually get a flat line on the other dimensions that you have controlled for, or that you think you control for. Okay, I hope the point is a bit clear. There are a couple of examples of kind of famous examples that do this kind of simulation. But let me go to the second type. Second type is like the first, just that we recalibrate control parameters. So we manipulate the same gender parameter in this case. And then after manipulation, we recalibrate the other parameters to the data set that was originally used. That safeguards that even in simulations, we get the same number of, in this case, ties, for example. So simulation design, we calibrate network model with homophily term. We change the homophily parameter in steps. We now recalibrate for each of these different scenarios, recalibrate all the other control parameters. And from these recalibrated models, we now generate outcome networks. Compare those on the number of intergroup ties. This is the result. It looks very much like the proper specification, the proper model specification with SimX. However, if we now take a look also at the total number of ties, this is what we saw before. This is how it looks like now. Now we really have the flat line because we recalibrated, meaning that we have a separate density term for each of these models, and that safeguards that we get the same density as we have in the data set. And so indeed we don't get artifact results in terms of the number of ties. Of course, the question is, are we prepared to study, to interpret this changed number of ties in the blue or in the red scenarios, are we prepared to interpret this as, as emergent outcome of the model? Or do we want to stay with a more empirical statistical way of thinking and say, well, no, we don't want to get this. This is an artifact. We want to control for this dimension. This is the whole idea why we have it in the model. So we should actually make sure that also in the simulations, it doesn't show any signal. And then it is not something on which emergence should be studied. Okay, but this is up to the researcher ultimately, what you want and what your aims are. There are a couple of published studies of this type, mainly involving people of the Siena core team, Tom or me, where this recalibration actually has been applied. Okay, now third type, just relatively quickly, I think this is kind of a different situation where what we manipulate here is basically the macro to micro thing. So the social environment in which our actors are sitting. So we have different input data. We use the same output, we use the same model, and we generate output under different input conditions. Simulation design would be step one, calibrate a model to an available data set, then use the estimated parameters, but vary the input data. In this case, because I'm again taking a look at intergender ties, changing the distribution of the initial intergender ties, and then see how over time our model transforms that into output intergender ties. Okay, and see how that manipulation, no, actually it's the opportunity structure that I'm manipulating here. So I estimate a model based on a 50-50 gender distribution, and the question is, what if there are very few girls or very few boys? So we have a whole spectrum, and we can assess how the same gender preferences in the micro model translate that input situation into a network structure towards the end, and assess how gender segregated these results will be. This is what I did in type 3. So I have actually artificial classroom data that probably don't exist in the real world. We will not find a school class with 20 boys and 1 girl, for example, but we have it in our counterfactual scenarios here. And here's what we see. It is sort of predictable. So in the middle, which is sort of the fraction females that was in the data set, I think 52% or so. So this situation here, we see that with fewer girls to the left or more girls to the right, from 100% girls going to 0% girls here actually, we see that in the middle we have the highest number of cross-gender ties, and towards the end we have the lowest number. Sort of logical, because there cannot be so very many if there are very few of either sex. So we see that back. It's sort of not a very interesting study, but it works basically. If we now study other outcomes, for example, the number of transitive triplets, which is the blue distribution, or the number of ties at all, which is the red distribution, then this also is quite sensitive to these manipulations, as we see. Okay, question again is, do we want this or don't we? In this third type of simulation study, well, we just get it. Okay. Always the question, are we willing to interpret some of the results as emergent phenomena, in this case density or transitivity, or not? Okay. There are a few studies doing this so far. I'm aware of this work by Jimmy Adams and David Schaefer, which actually mixes the manipulation of parameters with the manipulation of data. There are partial scenarios which only manipulate the data and not the parameters. So actually this is an example of this type 3 study as well. Yeah, I think this is, yeah, is there a take-home message so far? I think what is really important is that you need to know your models well. The message of is the effect centered or not? This is really a minor aspect of a model specification if you do the modeling for empirical purposes, but it makes quite a difference for simulation purposes because the parameter, this same X parameter basically covers component that, yeah, just is about modeling the number of ties, and it covers a component properly modeling homophily. And if you take a centered version, then this component which models the number of ties is actually separated out and becomes part of the density effect, which is the one effect that you think should capture this. So these kind of details require you to actually read up what the formula for each effect is in the manual and see whether there hasn't been some note above that all the effects are centered or not. So you really need to pay good attention to what exactly the effects are that you're manipulating, because everything is quite sensitive to issues like centering. If you have multi-period data sets, the question then is, are you centering for each period anew, or do you center around the grand mean? This will also make a difference. If you look at simulations, you wouldn't want to get artifacts because you misinterpret your effects. Then you need to think, second point, you need to think about emergence and calibration issues. If you have a model in which you account for control parameters, and from my point of view, the empirical point of view, this is an important, strong feature of these models, then you need to be clear about whether any change on these dimensions you would want to study as emergent outcome, as a macro level consequence of your manipulations, or whether you would want to actually account for this by recalibrating the model. These are really different approaches. We have seen this flat space. Do you manipulate your parameters in this flat parameter space, or do you manipulate the statistics that you generate in the curved space in higher order network space, basically? Whatever your choice is, now, of course, there may be good reasons for just manipulating the parameter and not recalibrating. You need to be aware of these things. And well, I say here, prepare to defend your belief. Basically, other people might think differently. People from the more empirical tradition might think you need to account for things in the calibrated space and not just manipulate single parameters. And then you need to argue for your choices. And this requires some in-depth thinking about what you consider to be emergent and not, and what not. Okay, I think that brings me to the end. I have one additional comment on counterfactual interpretation, but I would prefer maybe not to give it here. If we share the slides at some moment, it will be part after the last slides. So I'd be happy if you, if you had questions about this or comments.
Okay, what I suggest is if you just, just say if someone has a question and then we'll just call you. So Patricia is the first one to have a question.
Hi, thank you very much for a lovely presentation. I was wondering, kind of, I think I've studied network from a very different point of view, not from stochasticity, but from kind of empirical data and like collecting empirical data. And when you talk about calibrating networks to a data point that is, I assume, empirically established, so you have some data that would say, oh, this is the number of friendships between girls and boys in a school. Where do you typically have that kind of macro level empirical data point that you try to kind of figure out what are the homophily or kind of node attributes that would recreate this data point on the macro level?
Yeah, it should be sociocentric social network. And I call it macro now, but normally this is, it can be quite small social system. We have a lot of experience with school class networks, for example. And then the school class, actually these examples that I showed were from single school classes of size, I don't know, 25 or so, 25 actors. This is the macro level in this study. Of course, you could think of larger social systems, and in view of, for example, say, suppose you want to study friendships in a small city. Then what you can do with these models is actually just calibrate the model with calibrate the model with a known parameterization, like density, the number of ties you need to fit, the degree to which ties are reciprocated, and maybe the amount of triangles that people are typically involved in. If you get an estimate on these things on the ego level, then this actually already is sufficient for getting, say, this point in a three-dimensional space. Now, we don't really need the full complex network data for the whole city. We actually only need these three coordinates. So sometimes it's sufficient to get those by doing a survey sample and by averaging, and then we have an impression. Everybody has around 5 friends, so we have put the number 5 there. Or multiply this with the size of the city to get the total number of ties. And in a similar way, we can scale up from simple things that we know to expected values in the, say, in a population space. Even if the population is so big that we don't actually have a proper network data set there, this can be possible.
Thank you. Yeah, this is exactly kind of what I'm doing. So I'm working with kind of on the basis of a survey. I know more or less how many friends people have, how many colleagues people have. From a census data, I know the composition of a household, so how many family members a person has, and so on. But I guess this is, so for me, this is kind of quite difficult to do because there's a lot of homophily going on. I don't really know which homophily would make which matter in which case, because it's very context dependent. But yeah, but thank you. I thank you for a very good presentation.
Okay, I think we first had Kieran that had a question, and then I think we have another person after that. So Kieran?
Hi everyone. Thanks, Christian, for the presentation. I'm wondering, with regard to this recalibration, when or how certain can we be that something is about or more of a structural tendency versus a preference? So, like, if we're talking about gender homophily, do we know much empirically about the difference given an opportunity structure?
Yeah, I mean, for say the opportunity structure example, of course we do have sample data from a couple of school classes, but they will all be in the middle of these scenarios and not in the far ends where there are very few girls or very few boys. So in that sense, yes, the degree to which we can reasonably generalize, I think, is problematic. But how do you relate this to the recalibration issue?
Well, it was more about what you were also talking about with the centered parameters and preserving the density. Like, to what extent can we really say that we can knock out a parameter because we believe it is like a causal mechanism rather than a structural tendency that we're kind of, well, controlling out, let's say.
I think ultimately this is an issue of theory, that say the number of tiles that we can entertain, I think there are just hardwired constraints in the human, and probably you would have to rely on theories about this for arguing that you should not work with a model that in some scenarios gives you 2,000 best friends, because this might hold for Facebook, but it doesn't hold for best friendships. And and then I think the issue that you should recalibrate rather than treat this as an emergent phenomenon is settled on the theory level.
Okay, can we have time for a quick question still from, sorry, I'm going to pronounce the name completely wrong. Svevolot, sorry. I can see you, but you know, Svevolot, I think. Yeah.
Okay.
Yeah.
Firstly, really thank you for the talk, for giving me a stupid question, but at what point is it still an ABM? When we are creating an ABM with networks, we're manipulating only some kind of network characteristics on the macro level. Let's say level of homophily, or we still supposed to like think more about individuals on a micro level with their decisions towards homophily?
I'm not clear what the question is. I mean, these are two things. And of course, the one is sort of the aggregate of the others.
Okay. Is it still an ABM if we are manipulating only macro level, like homophily network, like in a whole model?
I see the point. So, say the big difference I try to make between the type 1 and type 2, do we have to recalibrate or don't we? And you would say that if we recalibrate, don't we actually hit on the macro level, while agent-based modeling is not about that at all? Yeah, well, I see the point of that, if that is your point.
Yeah, thank you.
But yeah, well, I think this runs under the heading of prepare to defend your beliefs. Now, if you are prepared to treat, say, these what I call artifacts as really emergent outcomes in an agent-based modeling tradition, then you need to make the case. Yes.
Okay. Thank you very much, Christian. Sorry for interrupting this beautiful discussion, and thank you very much for your very interesting presentation. I guess we will have plenty of time also in the next meetings to discuss questions like the one that Shevolod just asked about. You know, what is an ABM? If at which point in a network model is an ABM? Because this is the kind of discussion that has gone along pretty much in the social simulation community, I would say. So let me just introduce the next presenter, Kieran Mepham. I'm also hoping I haven't jeopardized your name.
No, it's fine.
Okay, who works at ETH Zürich. So Kieran, you have 25 minutes. Try to leave 5-10 minutes for Q&A.
Yep. Okay, can you see my slides now or not?
Yes.
Great. Okay, well, hi everyone. So I'm Kieran, as Federico just said. So I'm at the Social Networks Lab in Zurich. And actually, this is an example of the starting of a project using the stochastic actor-oriented model to, well, to run sort of an opinion dynamics kind of model. And this is work I've been doing with my advisor, Christoph Stadtfeld. So what we're trying to do here is build an ABM for opinions that's based directly on this empirical kind of calibration, which is something that, well, given the point of this workshop, I guess most of us are kind of familiar with the problems in just doing agent-based modeling without the kind of empirical part of it. Pavel Sobkovic has complained about the lack of dynamics. There's a paper that's slightly more recent complaining about the lack of empirical calibration of these kind of models in general. And with that in mind, we tried to start from a fairly simple question of whether our empirical model or empirically estimated model for polarization actually generates polarization in the long run. And we manipulate two things here. So this is the actual observed networks at the end of our observation period. I'll describe the observation a bit more later. And also from an empty network. So here we have a kind of data manipulation. There are a couple of other approaches that Christian has sort of covered here that he also showed us at a workshop last year. I won't actually go into these today, but I would like to play around with some counterfactuals, maybe keeping in mind some of the comments Christian has given now. But yeah, as I said, that's not for today, that's for another time. So we have a micro model, which is essentially what we're estimating through the SAOM. And there was quite a lot of groundwork that went into this. So this is a paper that's still currently in progress, but it's nearing completion now. So we estimated a stochastic actor-oriented model on multiple political opinions and with friendships as a social network, where we treated political opinions as a two-mode network. So if we look here at the blue circles representing individuals, we can have these purple squares that represent a attitudinal object, and people can then have a tie to the attitudinal object, either positive or negative, and a tie to one another as friendship. And within this framework, trying to look at the political opinion polarization type aspects of this, we focused on mixed triangles, so these mixtures of one attitudinal object, two individuals, and the ties connecting them, and these bipartite force cycles, so the configurations of two attitudinal objects and two individuals, and the kind of balanced opinions that the individuals have about the attitudinal objects. And to do this, we added some new effects to the Siena framework, which are actually all of the structures that you see represented here on the right-hand side. So the tendencies for actors to choose to have ties that are in these kinds of configurations. And we added some new goodness of fit auxiliary statistics also relating to these kinds of configurations. And essentially from the empirical model, it does fit on the key statistics that we're interested in, but the friendship network structuring is not perfect. So the data we used for estimating the model is from the Swiss Student Life Study, which is a data collection project which has been running for several years now, but is in theory closed. It reopened briefly as a result of the COVID crisis, as we wanted to find out more about our students, but it should be properly finalized now. And we, well, for the data subset that I estimated the model on, I used two of the networks of first-year bachelor students starting at the first week of their studies. And this is at a technical university in Switzerland. And I used 5 time points, so essentially spanning one academic year. I used a... Just a sec. Oh, sorry, I hear something in the background there. I used a battery of policy attitudes sourced from the German Wahlomat, which is basically a vote choice help. Sorry, I have a thing going off in the background. Sorry about that. So we used for the measures a battery of policy attitudes. We started with the German Wahlomat, which is a vote choice helper. So it just gave some hopefully salient political issues, which we modified with information from the Swiss referendum. So these Swiss referenda, they're mandatory, they're 4 times a year. And there's usually a variety of topics that come up in each referendum. So we thought particularly for this context, it might be more appropriate. And we just get an agreement measure, which is a Likert scaled 7-point completely discrete, completely agreed thing. And we also measured some demographic characteristics which we could use for controlling for homophily, on top of course, the endogenous tendencies that we expect to see in the friendship network. So for those of you who are not so familiar with the stochastic actor-oriented model as implemented in our Siena, basically what we do is we specify which statistics we think relate to the effects of interest. So we'll have the endogenous effects in the friendship network, so reciprocity, transitivity, and also the more interesting parameters from our perspective of opinion, selection, and influence. And then what the model does, it takes a network, well, two networks. You have your observed at time point 1 and you're observed at time point 2. And it kind of randomly goes through choosing actors, and then based on the current state of the parameters and the corresponding statistics that you specify in your model, the actor updates their outgoing ties, the chosen actor. And this is repeated for the estimated number of actions. And then at the end, you kind of look at your statistics, well, to what extent they resemble those observed at the end of the observation period, and you update your thetas in such a way that the statistic should be close to the observation. And effectively, you want to run your CNF model until you plausibly could have got from the observation at time point 1 to time point 2, given your parameters and the statistical effects you specified. So we get a huge table of results here, so I'll really quickly skim through this, but what we effectively have here is a lot of null results and some parameters that are in the wrong direction. Generally, we do see that the effects are stronger if they're in the direction of expectation. And we'll note here also that this is specifically for the friendship and opinion parts of the networks. If we move to just looking at the force cycles, so do people tend to converge or diverge on their opinions? The effects are consistently significant and in the expected direction. So it does seem that there's some sort of tendency towards maintaining or creating opinions that are congruent with the previous opinions two individuals have held relative to one another. So if I agree with you on one topic at one time point, it's also more likely the next time point I will agree with you on another topic. Alternatively, if I disagree with you at one time point, then I'm more likely to disagree with you on another topic at another time point. Of course, there are a lot of parameters here, and some of them really should be collapsed, but that is beyond my abilities. But to summarize, basically, selection and influence aren't significant in the current version of the model, and the polarizing or consensus forming aspects, regardless of friendships, are almost always positive and significant. I have, in the meantime, had to rerun the model anyway because well, it takes a long time to run. So now I'm writing up the final version of the empirical paper. And there we actually see that some of these selection and influence effects are significant, but they're not particularly strong. And if we think about it in terms of the simulation, it just uses the straight parameter estimate. It's not incorporating the standard error into the parameter estimate in some way when we simulate. Now we move from this micro model to the macro metrics. So what we want these metrics to capture two kind of theoretically grounded aspects of polarization, the ideological component. So this is something that we might see referred to as increased kind of constraint between individuals in terms like as Philip Converse would have used, or Baldessari and Gelman. So this is the clustering of agreement and disagreement on certain topics, regardless of the social connection between two individuals. Secondly, we do want the social component of polarization, as this is usually implied in the more network-focused studies of polarization, but is also implied in these identity theories into polarization, where we're talking about the social divide between individuals with opposing views. So this is how we do this in this bipartite network formulation. If we look at the first dimension, the opinion clustering part, we're looking at the number of congruent structures, so where people completely agree or completely disagree, to the number of structures where they only partially agree and partially disagree, plus all the congruent structures. For the social components, we look at the frequency, well, the relative frequency with which people who are not friends disagree, as we expect that people who are not friends are more likely to disagree than agree under a perfectly polarized network. and the counterpart where people who are friends should agree more than they disagree. Well, and since we have two of these terms here that range from 0 to 1 in theory, we divide them by 2 to give us the nice property that 1 is a maximally polarized network. So the nice properties here, I think, are that there is a simple interpretation, and the metric should range from 0 to 1. However, the first dimension can't distinguish between consensus and polarization at the moment, so it will need a little bit of tweaking. Because, well, if we look at the metric, just imagine the case in which everyone agrees on everything, then you'll always have a score of 1 on that dimension. And it's not possible, as far as I'm aware, to reach a polarization level of 0 under a realistic network. I could come up with some stylized examples with funny kind of ring lattices, but I don't think under a kind of reasonable real-life network we should see a 0 level of polarization. Now, moving to the simulation, the procedure, basically, I estimated the SAOM as I described earlier. I take all of the model parameters from in there, and then I run 100 simulation chains where I bump up the rate parameter, which determines the number of actions between observations at the last observation time point, so that I get basically the equivalent of 30 months forward simulation from the last observation of the network. And then at fixed step intervals, I just sample and check the macro level statistics, because it takes a long time to calculate, so I don't want to do that for every single simulation step. Now this carries this SAOM based, well, and also based on my data manipulations, there are some assumptions carried in this. So first, the social network changes, which is a good thing, because this is something that people are actually asking for. But also then that influence is channeled through these ties that change. We ended up trichotomizing our bipartite network of opinions. So actually we only end up with 3 possibilities between an actor and attitudinal object. So positive, neutral, or negative. We assume that people's sort of structural tendencies are static, they don't change over time. And another kind of important thing here, I think, is that the cohort boundary stays the same. So we assume that all the same actors are present in the network at one time, which we know is violated because people drop out of their degree program from which we took this data. And finally, from the more agent-based modeling side of things, there's a sequential one-to-one updating scheme that we're using for this. So as I said, we've only got partial results at the moment, and well, this is essentially what it looks like starting at the density. So this is just to give us an idea that it's generating a not ridiculous number of ties. We see that if we only look, say, 3 months into the future, yeah, and sorry, just as a side note here, so the observation is starting the simulation from the observed network is the turquoise, and starting the simulation from an empty network is the kind of red color here. We see that over the course of 3 months, everything still looks reasonable, although it seems like our opinions tend to go down. People have less opinions over time. Whereas after 30 months, we can see that there's problems in the friendship network. So this is a degeneracy issue, and it's likely because we included just straight transitivity parameters, which can lead to this kind of thing over time. It's the same as in an ergom. Often you want to include a geometrically weighted edgewise shared partners term rather than the combination of transitivity parameters that I've currently included. Looking at the densities of the positive and negative opinion networks, it seems that they do kind of converge around 1 point, but also generally that it's fewer opinion ties are observed in the simulation than in the real data, which suggests to me that maybe something is going on actually with the friendship network, that maybe the effects in the friendship network are just much stronger than in the opinion network. So people end up having to kind of avoid having opinions so that they can maintain their friendships. And this could then also perhaps be related to the degeneracy issue, as it seems that this occurs around the same time. But given that the parameters are very small for the selection and influence part, that might be completely wrong. So this is something that I'll still need to play around with. Now, if we look at the actual, maybe more the meat of this, the network polarization metrics, it stays relatively flat, especially in this first sort of 3 months part. And again, if we look at the observed, this stays in a much tighter range than if we start from an empty network. And that's just due to the stochastic elements of the model when it's kind of initializing in the simulation from the empty network. And yeah, we see a small drop off in the opinion clustering aspect of polarization on the sort of longer term. But again, it stabilizes around 1 point. And I think it's important to note here that we're in both cases quite close to the middle of the distribution. And perhaps this isn't surprising because it's coming from observed data on students who aren't notoriously a polarized subset of the population, unlike, let's say, Twitter users who are selected on their political affinities often. So for the next steps, I need to iron out this network polarization metric because there are a couple of properties that aren't so great. I would like to go into this counterfactual morass that that Christian has warned a little bit about. So we can consider what would happen if, say, selection and influence was stronger, but maybe then this should only be done on the parameters that are significant. And again, I think there's a statistical inference philosophy issue behind that choice. We could also consider what if these non-social opinion clustering forces were stronger or weaker, so the tendencies to become more similar or less similar over time, or both. And perhaps what would change if the friendship network effects were different, if there was no other kind of homophily, for instance, because maybe ethnicity, which we include in our model, also leads to sort of clustering of opinions in certain regions of the network. And I need to repeat this model because I only simulated on the basis of one of the two cohorts. And the other one is larger, so it will take more time, but it's nice to have a good kind of validation case. So thank you for your attention.
Great. Any questions? Wait, let me come back to real life. Any questions? Just checking. Okay. Nobody? Okay, Federico, what do we do? Shall we go on, or?
Well, I do. Well, actually, I do have a question. If everybody's shy about that, then I do have a question for Kieran, which is actually quite a general question on the on the opportunity to have simulations which are calibrated on empirical data in general. So you have quite implied it yourself in the beginning of your talk. There's quite a lot out there about political polarization. There's a lot concerning modeling and simulations, but they're mostly I wouldn't say abstract, but theoretically and not really empirically calibrated models. But and your approach has for sure the advantage of starting from from an empirical data set. But my question is, what are you losing? I mean, while you gain this in terms of empirical, let's say, realism, what is the extent of in terms of generalizability that you might lose by calibrating your model empirically?
I think there's two main things we can think about here. Is that there's practical constraints on what you can estimate your model from, and I think some of the theoretical parts of an agent-based model might consider, say, the change in a network over a number of years or something, which is not always going to be a feasible thing to calibrate your model on. And also now, of course, this comes from a model which is designed to estimate from empirical data, and so it has to do things that aren't necessarily going to correspond directly to something that you might think is a more plausible mechanism. I mean, we treat everything here as well, we have a tie that's positive, negative, neutral, but ideally we'd have a more continuous kind of opinion structure, and you can only estimate so many parameters from your data, which is another issue which you don't run into so much if you're doing the more theoretically based agent-based model. Yeah, it's largely practical constraints. This model alone, actually, even given the size of the second cohort, which is 600 something people, it's still quite hard to get it to converge. And I think that might also represent the fact that a lot of parameters go into this, and yeah, you have to be careful not to overfit and cause problems in that way.
May I also have a short question at the end, please? So the very typical of opinion dynamics processes in reality is that if you have certain friends, then you say, this is my opinion, and if you have another group of friends, you say that is my opinion. So there is hypocrisy in what kind of opinion I reveal to the others. And of course, these kind of models, you will always have a convergence towards a certain opinion. Can you see this in your data set, actually, that this kind of hypocrisy is actually prevailing or stable? And it's related to a question if the opinions are at least converging to each other at all over time, or there might be also a stability, a stable distribution in which they are going away from each other.
So it seems that there's not so many people that adjust their opinions completely from one side to the other, which is maybe a separate issue. I think what we should see is that it's more likely then that the people with a neutral opinion are more likely to change than people with an opposed opinion given a friendship tie, because it would be like, if there's a neutral thing, then if there's a neutral opinion from one friend, then there's a reduced cost of showing an opinion that might be potentially opposing from the other individual. Whereas if they're opposed and these two individuals are friends, obviously there would be a bit more of a cost. And I would guess that people can infer some of their friends' opinions based on other opinions that they know their friends to hold. But yeah, that's an empirical question, and also it then kind of goes into the more stereotyping kind of issues, and I think that might be captured a bit more by these 4-cycle structures. But this is also interesting empirical stuff going on here that I can't really get at the moment.
Yeah, I also have
okay, great. I am extremely sorry to interrupt this discussion, but we should really move on with the next presenter. I'm sorry, Rinkash, to interrupt you. I invite you, however, to maybe write your questions in the chat, or of course we can then circulate speakers' email addresses to go on discussing, outside this meeting. So thank you very much, Kieran, for this great presentation of an application of an empirically calibrated simulation model. So our next speaker is now Carlos de Matos Fernandes from the University of Groningen in the Netherlands. So I have Carlos has pre-recorded a presentation that I'm going to broadcast, but of course Carlos is here and can then participate to Q&A, just like the other speakers have done. So I have just, I'm going to broadcast the presentation. I've just shared my screen. Can you please help me out and confirm that you are actually seeing my screen?
Yes.
Anybody say yes? Okay,
Yes.
Great. So then let me run the presentation.
Hello everyone. I want to thank the organizers of this session for the opportunity to present here. My name is Carlos and I work together with Andreas Flache and Jacob Dijkstra from the University of Groningen. So today I want to introduce our working paper in which we zoom in on the issue in which groups with low levels of cooperation, we label them here as bad barrels, can spoil good apples. And a good apple is an actor who is pro-social and wants to cooperate when given the chance to do so. But such an actor can be spoiled when a member of a bad barrel, this uncooperative group, becomes less attractive as a potential new group member in the eyes of external others. And we expect this problem to occur when we include more realistic assumptions in our model and more information constraints. More specifically, if we move from full information to incomplete information. And then within the incomplete information framework, we want to argue under which conditions social networks may mitigate this bad barrels problem. So, first things first. Ideally, past achievements, skills, performances conceptualized as individual prior merit effectively signal an individual's ability. Examples include university project group formation, team-based payment schemes, and also organizational recruitment. And these examples have in common that individuals gain access to better groups based on their own effort and performance, which we visualized here. Let's say the orange one has a higher merit compared to the yellow actor here, so the orange one has a higher likelihood to join a better performing group. And we inspect the role of merit in the cooperation perspective, and in this area merit is related to cooperative or defective action. And ideally pro-social types have the opportunity to signal others that they are willing to cooperate, separating them from types who are more prone to defect, the pro-self types. And findings show that meritocratic matching works in this setting, and it can increase cooperation levels. But we argue that the same principle ideally holds for the situation where there is a large pool of individuals in the population. But this is particularly information heavy, requiring full information about all prior individual merit, and such information is oftentimes not fully available. And we may also not cognitively process information about all individuals when we want to form groups based on individual merit. Thus, in most cases and in real life, we must rely on incomplete information. And that's what we try to do here by relying on prior group merit rather than individual merit. So where and with whom you worked with in the past may be indicative of your individual merit, and it has way less severe information assumptions. So is relying on incomplete information, group merit, a solution? Our intuition is that it poses a problem of itself, the bad barrels problem. And we deduce this process from indirect reciprocity and learning principles. If others defect, then you're more prone to learn that to reciprocate the type of defective behavior that actors, even pro-socials who readily want to cooperate, may not do so due to others. And after reciprocating defection, presence in an uncooperative group reflects badly on its members, its constituents. So then we have a reverse basking and reflected glory effect. Good apples, pro-socials here, are stained by the group's ingloriousness in situations where they are matched based on only their prior group performance. And another theoretical argumentation for the bed barrels effect can be found in fundamental attribution error, where the lack of group success is most likely attributed to personal characteristics of the individual group, whether justified or not, may get the reputation of being inherently uncooperative, which may actually be due to the group. And we zoom in on prosocials in our model, who may not harness their full potential. For them, adding realism to the model may have a dark side, and we may lose their cooperative potential. But we also look into a potential solution for this problem. Actors do not live in a social vacuum. They are embedded in large complex social network structures in which information about one another flows. And these networks may also provide another way to differentiate between those who are prosocial and those who are not. And it also fits within our incomplete information framework, where we rely only on local social information, which we may use then as input for group formation and pair them with group behavior. And we extend our social network implementation by relying on another structural feature, homophily. So a homophily-based human tendency to preferentially form relationships but also interact with similar others may lead to cooperative clusters found especially in the theoretical literature. And it may allow us to, or the agents, to differentiate between who is actually cooperative and who is defective. And within this incomplete information framework, we argue that a spillover from social networks through group formation processes can be a solution for spoiled prosocial types. And we formulate three conjectures. So first, the move from full information to incomplete information leads us to propose that bad barrels spoil good apples. But then adding within this incomplete information framework that social network information may weaken this effect and allows agents to harness their potential as cooperators, the prosocial types. And then third, we argue that homophily may buffer this bed barrels effect even more due to quick identification of prosocials who can cooperate more often in the social network compared to the group context. And we do so by bridging the micro and the macro level. So we introduce more realistic conditions for agents to match to other groups, which we show here, 6 matching rules. And we gradually move from the information-heavy rule, rule 1, the full information rule, to a more incomplete information setting in a stepwise approach. And we, to inspect the role of networks, we compare scenarios in which we vary also the structural condition with social networks randomly formed, but also more based on homophily principles. And with rule 4, we test our bed barrels proposition. To test the propositions, we utilize an adaptive threshold model with stochastic learning components. And just short to introduce the model here, we have 2 types of agents, prosocials and procels. Prosocials are more likely to cooperate in the early stages of the game compared to procels. Agents are randomly grouped, and with the only exception rule 1. And during the game, during the group, here highlighted in gray, agents influence each other to behave in a certain way. Agents cooperate if enough others do so, otherwise they defect and update their thresholds afterwards, making more likely that an agent repeats past behavior that was associated with a satisfactory outcome and avoid behavior linked to an unsatisfactory outcome. And what we do next here is introduce a matching moment that they can join or switch to other groups. So if their threshold exceeds or is lower than group the average level of cooperation in a group, agents will leave, but if the so if the threshold is higher, they will leave. Then the average level, because they're not satisfied with the average level of cooperation in the group. So after they left, agents, which is an important assumption in a model, we allow them to show themselves in the early stages of the game. So leavers will rely on their disposition in the new group and allow agents to make a restart. So prosocials start with lower threshold, perhaps lower than compared to the adaptive threshold throughout the model. So we include a dispositional effect here. This decision algorithm governs both the interactions in the group as well as in the social network. So agents play an end-person prisoner's dilemma within the group, where all the behavior of others in the group affect their own behavior. And in the social network, agents play a two-person prisoner's dilemma with only one of their network partners, which they can switch with throughout the game. So at one point they play with neighbor A and the other with neighbor J. So how do we generate the social network? Then the social network is fixed, and agents are probabilistically linked to geographically nearby agents. So two agents who are more close to each other are more likely to form a tie than those who are less close to each other, and we do so by using the spatial random graph algorithm. We assign agents place on the grid, except for the structural homophily condition, where we assign prosocials to a predefined area, which is a very artificial way to make it more likely that prosocials form relationship with other prosocials. And we incorporate behavioral homophily for the interactions throughout the game, that only agents who behaved similarly last time, so cooperators with cooperators and defectors with defectors, they will play the game. So the input for the game, which is also now our baseline scenario, we are interested in settings in which groups remain fixed for some time, but they become dynamic at some point. The dynamic meaning here when they can match to other groups. So we try to mimic an academic year, in which students need to form groups for projects. At some point a new project may start. Students can leave or stay in the group for the new project, but at the same time students form friendship relationships with one another, which may or may not overlap with their group buddies. So students have two types of problems. They have a collective good problem, realizing a good group report in their group, but also forming cooperative social connections, like going to bars, helping each other move with one of their friends or their friendship group. And we try to mimic this situation in our model. Then some findings, preliminary. I have to say, but let's start with proposition 1. So here, the move from full information to incomplete information, we see that cooperation levels among prosocials drop radically over time. You see the spikes here when matching occurs, but they cannot cooperate at the level that they are striving for. So what we do see here is that bad barrels spoil good apples to not harness their full potential as a cooperator if we move from full to incomplete information. Then proposition 2, introducing social network information. If social network information is not available, because we only include local information, agents only rely on group cooperation levels, which is the same as on rule 4. What is interestingly here is that the mere introduction of social network information does not lead to substantial differences among prosocial types. So we see a slight increase of cooperation among prosocials, but it's only minor. So we can say that proposition holds a bit under this social network condition, but it's a very minor effect on the whole. Moving now to proposition 3, we introduced the same social network restrictions as on the 5, but the only difference here is homophily. The rest is the same as before. And what we do see here is that introducing homophily buffers the bad barrels effect substantially. So the possibility to preferentially link and interact with similar others facilitates a higher level of cooperation among prosocials in the group. And then another effect that I want to report here is what happens if we vary the percentage of prosocials in the population. So you see it here, 10 to 40% of prosocials present. And what you do see is that cooperation levels are the highest on the rule 1 and 2, the full information conditions. Then it drops on the 3 to 5, and then especially on homophily rule 6, that is sort of the best worst case when we move from full information to incomplete information. So what drives these homophily effects and also these full information effects? We found especially that prosocials tend to team up when they have the chance to do so, and they can identify one another, which may also explain why cooperation levels are so high among prosocials. So what we see here initially is that the degree of prosocials in the group is fairly the same. There are a bit more prosocial, less prosocials. There are more groups of non-prosocials on the matching rule 1 compared to 4 to 6. And there are a bit more prosocials clustering here, around 4 to 5. There are more groups with 4 to 5 prosocials. But then after all the matching, the picture changed. So in the gray area, you see way more groups without any prosocial, so fully pro-self groups, with 12 out of 20 under the full information assumption, and on average 7 when we allow for homophily. Then in orange we see that there are groups with 2 to 3 prosocials present in the group. Also 1, you see more of those groups when the information is incomplete. So prosocials can get stained by the average level of cooperation because they cannot team up. And here, this is a big factor here, is that prosocials can actually team up where they are in the majority and they can drive the level of cooperation in the group. So there are more groups with more prosocials on the matching rule 1 and 6. Another effect is the role of homophily. Homophily, interesting, does not increase cooperation among cooperative types. The levels are fairly the same, but it reduces cooperation of non-cooperative types. So when we allow for homophily, agents can differentiate between who is prosocial and who is pro-self. Because if you see here for rule 5, the cooperation levels are fairly the same. But if we compare for that you can only interact with similar behaving types, you see here that pro-selves tend to interact more with other pro-selves. They cooperate less. So homophily works because it increases prosocials' chances to join better performing groups compared to just random social networks. So to conclude, if there are more prosocials present in the group, cooperation increase. We also find over time that prosocials tend to group up over time, which also is an important factor for increasing cooperation levels among prosocials, and that homophily plays an important role when we decrease abstraction here in our model. Full information remains the ideal approach. Cooperation levels are the highest when agents have full information about all individual merit. But it is an information-heavy rule, a non-realistic assumption. And if we include a more realistic assumption and decrease abstraction, we see that only social networking information combined with homophily can solve some part of the problem in our model, especially when we follow the incomplete information assumption. But there's a downside. Less cooperative pro-self types, they may not cooperate as much as wanted. So some next steps, as I've been talking a bit too long, is do a thorough sensitivity analysis. Also challenge our new group assumption that you start with your initial threshold, and also change some other parts that we find interesting, for instance, other network topologies, keep a group fixed for a longer or shorter period of time. Looking forward to your comments. Thank you for your time.
Okay. I see there's already one question by Yunsub. So Yunsub, could you elaborate on your question?
Yeah.
Perfect.
Yeah, so what is the theoretical distinction of this study compared to the absolute emergence of cooperation? I mean, we're talking about the network effect or homophily effect, but any of the major scope is the cooperation emerges through some influence between actors or information they earn, something like that.
Yeah, so one distinction between the actual studies is their reliance on strategies, fixed strategies of agents. So we rely on a more adaptive threshold model where we incorporate contextual effects. And that is also one of an additional factor that differs also from the XOR studies, that we include these group effects, that you're nested embeddedness within the groups, as well as embeddedness socially. So I would say these are just two distinctions that I just came up with to answer your question.
Okay, any other questions? I'm just trying to go over 81 participants. It's very hard to see if you don't, so if you could put things on the chat, that helps. No? No questions? Okay, Federico.
Well, then I'm going, Carlos. I'm going to ask you a very similar question to the one I asked Kieran before, but of course on the on opposite terms, I would say. So I think a lot of people in the audience is more used to see kinds of simulations calibrated on empirical data, like the ones we have seen so far before your talk, while yours isn't really calibrated to empirical data. So my questions would be, first of all, if you can quickly elaborate on how you can handle this. I mean, you mentioned sensitivity analysis and stuff like that in your very last slide, and also, why this should be the case. I mean, why? Let's say you had empirical data to which to calibrate your model with. Do you think it would be worth to do it, or you would anyway go for a theoretical model?
Yeah, I would definitely go for the theoretical model because I have control over the agents. But no, we went for the theoretical model because we also want to compare this ideally to an empirical situation, and also formulate our propositions for the empirical situation where we have this setting. So we have this empirical setting in mind, but with students embedded within the groups, but also embedded within social networks. So we were just wondering if this empirical setting that we see around us, how that would interrelate. And we went now for the theoretical study as a precursor for the empirical setup that we hope to test our actual propositions that I mentioned here later on. Does that answer your question?
It does. Thank you very much. So I am sorry for the ones who have just written questions in the chat, but we are running out of time. Or maybe, so let me just introduce the next presenter. We have Yunsub Lee from Cornell University. Yunsub, thank you very much. Yeah. The floor is yours.
Okay, gotcha. Yeah. Okay, thank you for organizing this wonderful session. My name is Yunsub Lee, and I'm a PhD candidate in Cornell University. So this study is about the culture and opinion dynamics, agent-based model. And so, I mean, as you know, there are lots of the agent-based models of culture and opinion dynamics. I mean, they assume there is some when there is a simple micro actions, I mean, based on the social influence, I mean, ego becomes more similar or dissimilar to authors. Actors build ties with more similar others, such as the Devon Zetolas paper about the co-evolution paper, something like that. And anyhow, lots of papers focusing on some certain, under certain micro actions in social networks, some very unexpected and surprising macro outcomes, such as cultural consensus or diversity or political polarization emerge, something like that. So my scope of this study is, yeah, there are lots of studies focusing on micro to macro, but I am here focusing on the macro and micro. I mean, especially thinking about what is the social networks? Is it just a graph or more than a graph, something like that? So this study suggests the two formal parameters of social networks, which is applicable to most existing ABM of culture and opinion dynamics. And then I will apply these parameters to a previous model of the Flache and Macy, and then I will talk about how under certain macro conditions, very unexpected and dynamic outcomes of cultural or political polarization or consensus may happen. So I'm focusing on the two relational features of social networks, which are different from just the topological features, the strength of norm control ties and the induced homophily. And I will talk about why are the macro conditions as important as micro actions in ABM. So just let me briefly talk about the theoretical background. I mean, the agent-based modeling is a very efficient approach to explore the complex system of interdependent actions, which leads to a global phenomena such as the cultural diversity or collective actions. But rules of actions, as you know, in ABM must be sufficiently simple and localized. If it's too complicated, it's very difficult to track what's going on in the model. So anyhow, because the major explanandum of each model is the interdependent actions, not just the rules of action itself. So, but the problem is, I mean, the complexity from interdependent action is not characterized by the complexity of the rules of actions, but by the heterogeneity of actors, which is the really unique characteristics compared to the equation-based modeling. I mean, in ABM, actors can be really heterogeneous, and because, for example, each actor has a very different network positions and a very different cultural and opinion states, and it will determine the very complex system of influencing patterns or their actions or something like that. So due to your network position, actors' network position, actors' cultural or opinion status, actors may be more or less influenced by similar or dissimilar others, which makes actually very complexity of the model. So, but also the problem, the really key is the heterogeneity of actors can be the micro level reflection of the macro structure. Why people are heterogeneous? Because of the social structure, because of social networks, people have a different network positions, or because of some race structure or whatsoever, people tend to have a very different culture or opinion status. So this very close links from macro structure to heterogeneity of actors, their actions, and the emergence of the global phenomena. The linkage between the four actually shows some mechanism between how the macro structure leads to some macro outcomes, which is unexpected by the macro structure itself. So yeah, so from this point, yeah, macro conditions as important as micro actions. So I'm suggesting the two very interesting relational features of social networks, which are, as you know, it's not just the graph per se. I mean, so first of all, the strength of non-control ties. I mean, so the ties, if you have a relation with your friends, and if you and your friend have more mutual friends, then that relation will maintain longer. I mean, but if you and your friends have no mutual friends, I don't know. I mean, if you give up your relation, then it's really easily decayed, and easily it will be just you will fail to keep in touch with your friends if you don't have a mutual connections, something like that. So yeah, this is very basic ideas from the Coleman and Granovetter, because anyhow, if the two have a mutual connections, they will control all the morphisms, and they always encourage the very positive actions. So the relations will stay longer, something like that. So I'm actually suggesting very formal parameters of the strength of non-control ties based on the the conditions of the previous models. So simply, when there is a society has a range of the social norms. I mean, if all people have a very always the ties maintained, if each tie have 4 or 5 mutual connections, then and the range is 5, then this tie will always always maintain. But if the mutual connection is only 1, then the tie may be decayed, very likely to be decayed in the future, something like that. But anyhow, just to forget the formalization, I mean, anyhow, this reflects this type of the variation by how many mutual connections each tie have, and how much it determines each tie's strength of the strength, which is very structural. And induced homophily, I mean, in many agent-based models, homophily is considered as a micro actions. They try to find and connect with the very similar others. But as you know, institutions such as a school, job, and neighborhood are very segregated by the race, class, gender, and it actually characterize our networks more homogeneous. And I mean, especially the cluster network is getting more homogeneous. I mean, so here we are talking about the social agent-based modeling, and we are very cluster network. And finally, the people who are more interested in ABM finally have a cluster network, something like that. So these kind of things always happen in school, jobs, or neighborhood, wherever. So because of induced homophily, very homogeneous network, homogeneous and clustered network actually is structurally emerging. The point is, when specific race or class are homogeneous, have a homogeneous network, at least some portion of their cultural or opinion states will be very similar, not because of their interpersonal influence per se, but because of the very inequality of the society by race, class, gender, something like that. So yeah, this formalization is based on this idea. So if there is I mean, usually the ABM models assume people have a very random distribution of the randomly assigned cultural or opinion status, but under the formal condition, they tend to be very biased. I mean, yeah, let me explain it with some examples. So for example, in this network, as you see, the blue group is some clustered and the red group is clustered based on the block modeling analysis. So if induced homophily is conditioned and that there is a two-dimensional cultural and opinion status, but one dimension, the first dimension is affected by the class, race, gender kind of induced homophily, then yeah, all the cultural and opinion states follow the uniform distribution between -1 to 1, but red group will tend to follow -1 to 0. I mean, but blue group will have a 0 to 1. I mean, this is like this. I mean, so some people, I mean, such as the some lower class people may like this some certain types of foods, and some high class people like certain types of foods. So because of that, there is some difference of their cultural taste. But they also share the very randomly distributed cultural taste, with something like their taste about Asian food or specific ethnic foods may be very just randomly assigned, not based on their class. So yeah, this reflects this type of the segregation of the cultural taste based on the segregation of the race by race, class, gender, segregation of network race by race, class, gender, and this is clustered. And the strength of the norm-control ties, I mean, especially, for example, if there is a range of norms in the society is 3, and then the tie between 1B and 1C always stay permanently because they have 3 mutual connections. But on the contrary, the tie between 2D and 2B will be very likely to be decayed because they have no mutual connections. There's no friends who control their morphisms to each other. So they will easily lose their friendship. So I apply the 2 parameters to the previous model, Flache and Macy. So I actually maintain all the conditions of the micro level and some topological condition, I mean graph level conditions, small world, something like that. But I add the ST and IH conditions. And the previous model shows more polarization by more long range ties in a small network. But I'll show how much it become differentiated by the 2 when the 2 conditions are added. So yeah, this the left one is the Flache and Macy model network graph. I mean, each actor has a 2-dimensional cultural and opinion status, which are randomly assigned, and all the ties are fixed and the permanently always be maintained. But under my induced homophily and strength of non-control ties conditions, so each cluster tends to share similar cultural opinion state, only 1 dimension, the 2nd dimension, but they also share the very randomly distributed cultural and opinion states. And the ties in cluster always maintained, but the long range ties may decay in 0.01 in 1% probability. And when usually just 1 or 2 ties are decayed each iteration, but also rewire randomly, not based on personal preference, but based on the random connections. So anyhow, long range ties always will be decayed and rewire again and again under the condition of ST. So in the first part, actually, I apply each parameter separately, and there is no really interesting result. So as I said, yeah, the previous model shows some polarization by more long-range ties under the process of the xenophobia and homophily. I mean, similar people will become more similar, and the dissimilar people will become more dissimilar. Something like this. Under this influence, this assumption, polarization happens. And yes, under ST or IH, still polarization happens, although some level of polarization is different, but anyhow, the tendency, I mean, polarization tendency is still same. But when the two parameters are simultaneously applied, very interesting outcome emerges. I mean, randomly, it shows some very extreme polarization, showing the correlation between the two cultural or opinion status, or it shows very extreme consensus by showing the very lower level of the polarization. So I repeated this simulation 100 times, and this is the frequency of the equilibrium polarization measures after 2,000 iterations for each simulation. So as you see in the previous model, yeah, all the simulation tends to show 0.5 polarization. So yeah, this is very fair. And when SPA is applied, still more polarization happens, but anyhow polarization happens. Yeah, I mean, there's no difference from the previous one. And the IH, I mean, induced homophily is applied, some consensus happens, but anyhow, still most of them are polarized. But as you see, when both parameters are applied, very extreme level of consensus or very extreme level of polarization happens. I mean, the probability of the being consensus or polarization is polarized, literally. So my point is why this happens. I mean, it's very interdependent situation of the macro conditions, which is very unexpected. So in the second experiment, I changed the variation of the ST and IH, and especially so strength of tie. Under the first condition, all ties are fixed eventually when each tie have only one mutual connection, and under 0.015, some cluster ties may be decayed and rewire, something like that. And in the IH condition, there is no segregation. I assume there are 4 dimensions of culture and opinion status. And under some cases, it's maybe strong segregation. I mean, 3 dimensions maybe correlate by or segregate, but if because of race class or zero, or there is no segregation happens, something like that. So I changed this variation. So when there is no segregation of culture by race, class, gender, just the not interesting thing happens, just the consensus. But when some certain level of correlation happens, I mean, some high class or low class may have some similarity, then consensus really easily happens. And the point on the also interesting part is when long range ties and cluster ties are decayed under this condition, some cluster ties decays and rewire, then some variation happens. But only cluster ties maintain and the long range ties some change, then there is no variation, only extreme situation happens. This is same when the correlation, when the segregation of culture by race, class, gender is very strong, because only extreme level of polarization happens when clusters are fixed but long range ties are rewired. Really extreme case always happen, but when some cluster ties and long range ties are rewired both, then some variation happens. So my point is, from these findings, it shows stable clusters of simulation plus unstable long range dissimulation is the key. I mean, if you always got the positive or become similar with your close friends, but you always interact with very randomly with other people in other groups, something like that, then some extreme polarization or consensus may happen. Here are some scenario. I mean, so when the randomly assigned cultural opinion state and there is a correlation of the class and race gender, there may be some extreme actors may exist. or not. If there is some extreme actors may exist, so a simulation process in a subgroup will yield, so for example, if you always connect with the high class people, you become more high class people. And if you lower class people always contact with the lower class people, they will become more lower class people. This type of two simulation process may increase the assimilation between the two groups because they may share some certain commonality. But in some cases, it may yield some dissimilation. And the point is, a randomly assigned or cultural taste, maybe assimilation will be boosted when the two groups are becoming more assimilated, but it may be very dissimilated because of the more repeated assimilation process in each group. So in this case, very randomly assigned cultural taste become a new distinction between the two groups, such as covering or wearing mask become a new issue of the cultural political meaning to liberals and conservatives. It emerges like this. So this process may show the something like this, a complex process of how some randomly assigned or non-political or non-group issue become a group issue between the two. So the findings provide a potential explanation of the why the very severe polarization or conflicts happens, though some cultural tastes are quickly diffused and accepted, even if the network structure is the same and the individual actions follow the same group. And so from the findings, it also suggests a different perspective of social networks. Social network is not just a graph, it's more than a graph. And this modeling approach maybe contributes to building a network theory of opinion and cultural dynamics. And so because macro conditions may be complementary, and we can suggest more and more macro conditions and talk about and share some common macro conditions to develop the models. Thanks. Yeah. So.
Okay, great. Thank you. Any questions? Or let's see. I don't see anything, but no questions, or am I missing something? Federico. Oh no.
Actually, I heard Martin Neumann.
Martin, yes.
Okay.
Yeah, but you were first, so please go.
No, you go ahead. You go ahead.
I just have a simple question for clarification.
Yeah.
When you said norms, I didn't get the point exactly where the norms come in your slides on norm.
Yeah. So norm is very likely to exist when two people share mutual connections, because they control each person's some Murphysians, or they always encourage them to do some positive behavior to each other. This is based on a Coleman's idea or ground of Vettel's idea about the structural embedding, something like that. So, the point is, whoever the actor under that situation, the tie strength is very structurally determined. If a tie is embedded in the dense connections, they always maintain whoever the actors. If the tie is embedded in sparse connections, they may lose their connections because of the sparsity, like that. Yeah.
Yeah, thank you.
Yeah, thanks.
Okay, Federico?
Yep.
Hi, Yunsub. Thank you very much for your presentation. So if I understood correctly, rewiring of clusters rewiring of within cluster ties does play quite an important role in the explanation of what's going on in your simulation. So I was just wondering, maybe a naive question, but I was just wondering, how realistic is that to assume? What? Well, it's not an assumption. Sorry, but at what extent can we expect? How often can we expect within cluster ties, which are usually strong ties, you know, to rewire and how.
Yeah, I mean, so my point is that in each cluster, the cluster ties always, it's easy to assume that cluster ties will maintain longer than the connection long range ties between clusters. Is it correct? Because of the structural reason, right? Yeah, I mean, under that situation, which is very reasonable because of the structural and the norms, and something really unexpected thing happens because, I mean, if under the stable influence from cluster ties, we always become similar, maybe easily following other people's, our friends' ideas. And yeah, that will happen in each cluster. Always, all people will follow their cluster ties, some kind of friends' opinions or cultural taste. But from the very rewiring long-range ties, we become unexpectedly polarized, something like that. So, and this is not because of our personal choice per se, but because of some structural reasons of the stability or instability of the ties, something like that. So, I mean, I think that this model is more realistic. I mean, this is because it assumes it reflects the more relational features of social networks, not just the topological condition only. So, yeah, something like that.
Okay, I don't see anyone else having any questions. So Federico, do you want to close the session? Or
yeah, so yes, so thank you very much. I think we can close the session. Let me, and so thanks to Christian, our invited speakers, thanks to Carlos, Kieran, and Yunsub for their presentations. Let me just remind you that we are still meeting tomorrow, same time, so 2 p.m. Central European Time. Just another Zoom meeting link. You can find it on the PDF that was sent to you by the organizers. And let me also please remind you that we are still having 2 events today within the Social Simulation Week program, and namely, so at 5 p.m. Central European Time, we have Flaminio Squazzoni, the editor of JAS, the Journal of Artificial Societies and Social Simulation, who basically meets authors and readers of JAS. And then following that, at 6 p.m. Central European Time, we have an invited plenary talk by Anima Anand Kumar from Caltech, who will tell us how to create generalizable artificial intelligence. So see you there, or maybe see you tomorrow at 2 p.m. Thank you all.